Okay, we are doing a set of information here where we're introducing vectors. This is the first part of that. So our basic topic today is that of vectors. Okay, so a vector, usually drawn as like an arrow, is something that has two quantities that are established to it. So a vector is something that has two mathematical qualities. It has what is called a magnitude, which we tend to mean is like its length or how far it has traveled or to what degree has it moved or changed, and then also a direction. So let's call this vector v. So denote that with an arrowhead. Sometimes when you see it in print, you'll just see the v as being bold-faced. So that's your vector. This has a direction. Its magnitude would be its length or how far it has gone. We tend to write magnitude with a single bar. Okay, so this is magnitude. Magnitude. There we go. The idea here is this is a scalar, so this is going to be an element of the real numbers. The correlation here to absolute value makes sense because if you take a real number, its magnitude is how far it is from zero. So absolute value is a type of magnitude. It's not the be all and end all. Okay. So sometimes we use vectors to represent displacement. So we have things that are called displacement vectors. So this would be a physics application of a vector. So if we have a displacement vector, in this, the magnitude of the displacement vector is how far a particle travels. So like looking at our vector v, if I went from here to here, this would be how far it traveled, and the magnitude would represent that distance, and then you get the direction. So what's interesting to note about a displacement vector is it can be kind of freestanding in space. We know that it starts at some point. We know that it ends at some point. We have an idea of how far it has traveled, but we don't know where those points are. So we have a sense of distance and direction, but position is irrelevant. Okay? So in some ways, if I have a displacement vector that travels from point A to point B, okay, so here's my displacement vector traveling from point A to B, right? I can denote that the displacement vector r is the same as the vector traveling from A to B. So we call A the initial point, and we call B the terminal point of the vector. Okay, so we're starting to create kind of an algebra around this. So in order to make an algebra, you have to have an idea of equivalence. So we need to be able to say when are these mathematical entities, vectors, equivalent. So when do we have equivalent vectors? Okay. So let's say I have a vector u and I have a vector v. Okay, so when are they equivalent? So if the magnitude of u is equal to the magnitude of v, right, then that's part of it. And u and v have the same direction, then we can call them equivalent. Okay, so we write that u is equal to v. Okay, that seems pretty straightforward. Nothing too over the top there. That's something that you might want to recognize, is that when you have equivalence in vectors, you do get three properties. You get, or equivalence in anything, you get three properties. You get a reflexive property that says that everything is equal to itself. You get a symmetric property which says that if u is equal to v, then v is equal to u. And you get a transitive property which says that if u is equal to v and v is equal to w, then u has to be equal to w. Every single equivalence relationship has to embody those three properties. In order to form an algebra with vectors, we need to throw in something here because it doesn't fit with the normal form. We need to throw in a zero vector. And so ultimately, having a zero is not always a simple thing, and sometimes it needs to be defined independently. So if I have a vector that is a zero vector, then the one thing that has to be true is that its magnitude has to be zero. So this is the zero vector, this is the zero real number. That has to be true. So we're creating kind of a mathematical fiction here of a vector that has no magnitude. Note, the zero vector also has no direction. If it has no magnitude, it's not going anywhere. So it's like, in what direction is it going? Nowhere. Well, we just kind of think of it as not having a direction at all. Having a zero vector is going to allow us to get to an idea of addition and subtraction, so we're going to get there. Okay, so let's take a look at what is vector addition. Okay, so right now, the only representation that we have for a vector is kind of an arrow. Okay, we don't have any kind of Cartesian or numeric representation at all. So let's say I have two vectors. I have one called u and one called v. Okay, and u runs this way, and I'm going to put v in a very particular place. I'm going to start, so u has its terminal point here. I'm going to make that the initial point of v, and I'm going to put v here. And remember, vectors don't really have a fixed position, so even if u and v aren't in these positions, I can move them so they are like this, and there would be no sense of me changing anything. Okay, so we're going to define addition as being this vector. So if I add vector u to vector v, I'm going to get this vector kind of running through the middle there. Okay, so if I some people say that this is like tip to toe, or if I go from terminal position to initial position, and then the vector that runs along here is what we call the sum vector. So you add two vectors, you get a vector back. So when we create a mathematical entity and we do addition, one of the first things that we want to check when we have an operator is whether or not it commutes under that operator. Now, like, that seems like it should always work, but it really doesn't in reality. We're gonna find, like, when we get into linear algebra, that matrices do not commute under multiplication. So this is something that you don't need to know at this point, but like if you did a course in abstract algebra, you would learn that there are things that are called abelian and non-abelian groups, and vectors under addition are an abelian group because they commute. Matrices under multiplication are a non-abelian group because they don't commute. Okay, but what we need to know for right now is that vectors commute, okay? And they commute, and we can use something that's called a parallelogram law. To show that law. Okay, there we go. Let's fix that law. There it is. Parallelogram law to show that vectors commute. So a minute ago, we took a vector u, and we brought in a vector v, and we said, okay, this is right here. I'm going to draw an arrow to it because it's going to get crowded here in a minute, is u plus v. Okay, so the question is u plus v the same as v plus u? Well, if we start at the same point here, and maybe to make my point, I'll grab a different color. Let's use pink. All right, so if I start here at pink, and I now make a vector v, and then connect that to a vector u, right? So, oops, not that one. U, this one's u, right? So you can see, because this is a parallelogram, v has the same direction and magnitude as this v, and u has the same direction and magnitude as this u. But see, now in this case, this same vector, this vector kind of coming up the middle, right? That same vector is now v plus u. All right, so that's v plus u. So here you get that v plus u and u plus v are in the same vector, so the parallelogram law should say that u plus v is equal to v plus u, because they have the same direction and magnitude, even though I switched the symbol. So what we have here is that vector addition ultimately commutes. Okay, so let's just do a quick summary of what we have learned today about vectors. Okay, so vectors are things comprised of a magnitude and a direction. Other things that are going on here, that you can use vectors at this point. Generally, we're using them to represent displacement. It's not the only thing that they represent, but it's a common thing. We have thrown in there what are equivalent vectors, which are things that have the same magnitude and direction. So they don't have to have the same position. Ooh, that's bad. Vectors. V-E-C-T-O-R-S. There we go. They have to have the same magnitude and direction, but they don't have to have the same position. So that's important. We created kind of this mathematical fiction called a zero vector that has, I don't know why I want to put an I in that word. A zero vector that has a magnitude of 0, but no direction. So the magnitude is 0, it has no direction. It's the zero vector. It's going to come in handy when we do addition and subtraction. And we got this idea that if I take a vector u and I attach it to a vector v, Then the thing coming across is u plus v, both vectors, and that the vectors u plus v is equal to the vector v plus u. That one's the v plus u, and we called this the parallelogram law, and that establishes a commutative property for vectors.